Okay, so this is the CF Turbo presentation, and then we're gonna have the ANSYS presentation video thing afterward. So, I mean, I'm sure you guys all know basically what CF Turbo is. Uh, it's a software that lets you design turbo machinery components. So your impellers, your volutes, your inducers, your stators, everything like that. So specifically with us, we're using them to design our impellers and volutes. So the way this works is the first thing that you're going to see when you open CF Turbo is you're going to get this global setup window. So here you put in some parameters that are going to define basically that are going to be constant throughout every component that you put into the system. So these are things like mass flow. So and then you can also choose, you see how it's a drop down with the mass flow. You can also choose to put volume flow if you have that data instead. They're related by density, so they're essentially the same thing. The same thing with, you can put in your head value, which is the amount of feet that your pump can pump vertically upward, or you can put in your delta pressure, so the pressure difference that you want your pump to be producing. That's, the pressure out minus the pressure in. Um, and then on the right side, we have some values that are kind of important to keep track of. The big one is going to be power output, because you take your power output and you multiply that by a bunch of your efficiency values and you get your power input. And your power input is important because that's how we size our motors and um, everything like that. So yeah, on under fluid, you can put in your fluid name. It's ethanol, but because CF Turbo is kind of weird, it doesn't show it. You also can't, in the newest version of CF Turbo, you can't add new fluids because it is a little iffy, it breaks. But that's why we've been passing around the file that has ethanol in it instead of adding it, because you can't actually add it. But yeah, and then obviously you can set your inlet conditions, pressure, temperature. That's Temperature is more important if you're using locks, because you don't want to, or your inlet conditions have to have locks at liquid, so you have to mess around with temperature. Um, but yeah, that's basically it for global setup, I think. Are there any questions about global setup? Anything? All right, then we can go on to main dimensions. Um, so basically, this is going to be where you build out the basic skeleton of your impeller. So you get your dimensions. Um, oh yeah, we want to take a nice like video thing. Okay, so yeah, basically, as I was saying, you get your dimensions. So your diameter, your width, your hub diameter, eye diameter, or I think this one calls it hub diameter. They're basically the same thing. Um, and yeah, some of the important things about this main dimensions page are the Cordier diagram, which is this green thing right here. It relates impeller diameter and RPM. And it has this green zone here, which is like your efficient zone or your optimal zone. So that's why this is important, because it can basically tell you, given 30,000 RPM, what range of diameters that are going to be efficient or like acceptable for us um, based on our global setup. Um, we also have some check boxes here. So if we want to have splitter blades, this is where we're going to add splitter blades. If we want to have, we want to choose unshrouded impeller, so the shroud is separate from the hub and the blades, then we can do that here. And then if we had inducers, we'd be able to mess around with the multi-stage options. So we could decide energy fraction. So 20% of our energy is going to the inducer, for example, and 80% is going to the volute. And that's it for the setup page here. If we go to parameters, this is basically how CF Turbo is going to calculate your dimensions. So it uses a bunch of these dimensionless parameters that are sort of set based on your initial conditions from the global setup. So intake number, which I'm honestly not sure precisely what intake number is, but it's related to your suction diameter. Work coefficient, so that's a dimensionless parameter that informs your impeller diameter. So this, in combination with your Cordier diagram, is going to give you your impeller diameter. And then you have outlet width ratio, which is basically given your diameter, how like thick or how much space should there be between the shroud and the hub of your impeller at the end. So that's the ratio there. And then we have efficiencies down here. So hydraulic efficiency is based on the correlations that you can find buried in CF Turbo. And I'm assuming they're, as best as they can make them, obviously, but these values are correlations, so they might change a lot based on when we get into testing. And then, yeah, as I said before, if you have you have the power that your pump is outputting, and then you take these efficiencies, you can find the power that your pump needs inputted into it. And then that's important for motors and stuff. And then the last tab on this page is dimensions. So here we have our shaft calculations. So we have allowable stress, factor of safety, and then it calculates a minimum shaft diameter for you. And then, yeah, I don't know if we want to go larger for our shaft that we're sending new motors. I think that's more the shaft people.
Is that allowable stress from material property?
Yes, this is based on steel, and then you basically take your power that you need to input into the impeller, and you know your RPM, you know your power, so you can find your torque. And then based on your torque on the shaft and your material properties, you can find the minimum shaft diameter. And then I have a Python script that does some of this math, and it checks out. This is, yeah, it's just basic 204 math. And then for main dimensions, these were defined in the parameter section. But yeah, basically your hub diameter is going to be, if you imagine an impeller, it's going to have like chalk. Unfortunately, the recording people might not get this, but if you have your impeller thing, here's like a rough idea. So this is your shroud, S. This is your hub, H. Your hub diameter is here. This is fluid doesn't come in here. This is where maybe you put a bolt or something, and then you attach your shaft to it. Shroud diameter is here, and then your fluid comes in around the hub here. So yeah, suction diameter, I think they call it suction diameter in CF Turbo, that's here. And then impeller diameter is obviously this one. And then, yeah, outlet width is here. So this is your outlet width. This is your diameter. So these are the basic dimensions that it calculates in this stage. And yeah, oftentimes when you get these dimensions, I'll make some modifications to them sometimes. As you can see, there's the beta angle calculation that goes along with this diameter. and it's 0 degrees right now, which is throwing an error. That is something that we'll obviously need to change because CF Turbo is coming up with some math that doesn't make sense. So yeah, sometimes I'll mess around with this diameter um, to allow for better blade angles, and then we can work on the blade angles to reduce turbulence. So here is your, I don't know how to say this word really, meridional contour. So this is like if you took your impeller and you got a cross section of just 1/2 where the fluid is flowing. Um, this is all automatically done for you, and most of this stuff I don't change. But the important part here is this black line is the what your blade looks like when you're designing it. And oftentimes this black line will have curves added to it, and that impacts our manufacturability because if we have a weird looking edge to our blade with like overhangs and stuff, then it's much harder to manufacture. I mean, we can still 3D print it probably, but I change it to always be sort of vertical to just aid in the manufacturing process and make sure that whatever happens with the 3D printing, we can still get the impellers done here. Blade properties. So here is where you get the actual design of your blades. So the important things here are we want to choose 2D axial because if you choose freeform 3D, that means it's going to determine what your optimal blade shape is in 3 dimensions. And what that usually results in is really weird looking blades with all sorts of curves and twists in them that aren't manufacturable. So we set it to 2D, so it's only looking at the XY plane. It's not having the blades bend and twist as they go outward. So that's why we set that. Leading and trailing edge thickness. This is usually left default, but I'm going to try to do some FEA to figure out what our thicknesses should be and make sure they all line up with what we have here. And then the important part for turbulence is this slip window right here. So the slip model, we usually choose the default, which is Gulish Wisner. And slip is essentially the deviation of your fluid flow from your blade path. So you want to reduce slip because if your fluid is deviating a lot from your blades, then you're going to get turbulence. So what you can see here with this curve is this is looking at your slip as a function of blade angle. So slip on the Y, blade angle on the X, and it has minimum values. This is sort of this local min for the slip value here. So that's why beta B2 is 26.4 is because the slip model tells us 26.4 is optimal. We could technically choose 159.8 because that's like 0 slip, but I've found in testing that if you go beyond 90 degrees or below 15 degrees, it might say you have 0 slip, but when you run it in ANSYS, it has tons of turbulence. So yeah, that's what I try to keep things between 15 and 90 degrees for the beta B2 angle. That's the trailing. That's like your end angle. So I should like sort of draw. There's like, if you have a blade, you have your like initial angle. This is B1. And then the angle here is 2. So that's the angle we're referring to. And then beta B1, I mainly keep it just automatically calculated because usually that initial angle is based on your swirl factor coming in. So how much the fluid is spinning, if at all, and you want to have the initial tip of the blade contact the fluid at an angle where it sort of smoothly merges with the fluid. It doesn't cause a lot of turbulence right there. So yeah, that's what the angle sort of that's what the angles mean. And that's sort of how I work with building up the angles based on the slip factor. And then once you got your slip factor figured out and you have your blade angles, this is your blade mean lines. So this is the actual part where you get to see what your blades look like. Um, the important thing here is obviously you want to have smooth graphs. So sometimes CF Turbo will give you blades that have weird like wiggles in them or something like that. That's obviously not good. So we want to make sure our progression between our angles is smooth and our progression over the course of the blade, it sort of smoothly transitions between the two angles. Also on the right, we have wrap angle. Now, what I found is that wrap angle is useful in reducing turbulence. So if we have, I'll just draw it on here again. So if we look at a blade and we like take this here and then this here, and we like just look at like what angle of the circle this blade is taking up. This might be like 90 degrees wrap. If we start here and instead of going to this point, we go to a point like down here, but we keep the same angles. I don't know if those are the same angles or not, but assume the angles at the start and the end are the same. We have a greater wrap angle. So that's like 35 maybe now. So that's basically all that wrap angle means. And what I've found is that keeping the wrap angle around 135, maybe a little more, but maybe a little less, but roughly around 135 is helpful in reducing turbulence. That's what I've found the most success with for our ANSYS runs. And yeah, that's basically the important parts of this page. There's different design modes you can choose, but I usually go with conformal mapping because it's the default and it allows me to mess with the wrap angles, which have proved helpful in reducing turbulence. Blade profiles, this part is pretty simple. It's just your thickness of the blade. And if you wanted to, you could have your blade increase in thickness as it progresses outward. But right now, I have it kept as a constant thickness throughout the blade because I haven't really seen any benefit from changing the thickness as we go along the blade. And that's pretty much all that's done here. And then blade edges. So if you look at the blade, what's the edge of the blade going to look like? So some designs are tricky in ANSYS because if they poke out a little bit uh, from the impeller diameter, then ANSYS crashes. So I've found these blade designs work really well. Yeah, they're kind of sharp at the front and they don't cause a lot of turbulence when they hit the fluid. So yeah, I just like these shapes for blades. And then we'll go over to a little bit of volute stuff. So basically what we want to do with the volute is we want to match the diameter of your impeller. So the outer diameter of your impeller is going to be very close to the inner diameter of your volute. You can use this arrow here in ANSYS that automatically selects. It pulls in your impeller data and automatically fills in some of the fields for your volute. So you don't have to copy over numbers, it'll do it for you, which is really nice. When we look at volute cross section, we can define what the actual cross section of the volute is circular is the default, but there's all sorts of designs that are a little bit more efficient. There's one design that kind of looks like this. I don't know how manufacturable that is, but it increases efficiency, at least according to CF Turbo. So that is something that maybe if we're 3D printing or something like that, we can use a more optimized volute cross section. For spiral areas, this is basically how your spiral is going to progress. So you can define basically it's going to start at some value close to zero or at zero width, and then it's going to slowly increase until you get to your outlet. So right here, it's linear, and we define the outlet height. So it knows how to build out the progression from there, just starting from zero, going to 360, and starting at zero height. Well, they call it height here. It's basically the cross section width, and then starting at zero and going to 0.4 inches. I chose 0.4 inches because it gave me reasonable efficiencies, but that number isn't set in stone. That's sort of just, I picked a number and it worked pretty well. So that's maybe something that we get some more finalized numbers on with the volute sizing. Diffuser is the bit on the end of your volute. It converts some more of your kinetic energy to pressure energy, which is what we want. We want a high static pressure coming out of this volute. So yeah, I set the diameter to be 0.5. I don't exactly know our line sizes yet, but we can mess around with the diameter so that it fits with our line sizes there. And then, yeah, I mean, a lot of the diffuser parameters I've just left them default because I have no reason to really mess with it. But yeah, this is obviously the part that's going to connect to our tubes, or yeah.
Is it possible to have the diffuser kind of go out of the page a little bit? Go into like, let's say the Z-axis, if we wanted to make it better for packaging. I know that's just one thing we are thinking about doing.
Like have the volute here and then it comes out like that.
Yeah.
I could look into that. I haven't seen that yet, but I could try and figure that out.
Exactly.
Because that might help with packaging. I don't know if the bend there would.
That's what it, yeah. Jen, just did it.
It works?
Yeah. That's sweet.
Oh yeah, you can bend it there. Can you do like 90 degrees or is there a limit to that?
Oh, awesome. Okay.
Okay, so we can get it done that way. Awesome.
Good fun.
All right, so we can, yeah, I guess we can mess around a lot with the diffuser. We can point it 90 degrees. Yeah, I'm. Yeah.
That's pretty much a tube bend.
We just have it simulate the entire tube.
Yeah, we just throw everything in there.
Yeah, you just have
Maybe we could model the volute like this and go to a certain diameter and then we just do the tube bend. Because otherwise that looks hard to manufacture.
If we're 3D printing.
If we 3D
Even 3D printing, it's going to be interesting.
Yeah, it was an idea. Let's we can look into it later.
Yeah. All right. So cut water is basically where the spirally part of your diffuser meets your meets the volute basically. You just want to make sure that this sharp point is sort of not causing a lot of turbulence in your fluid. this is going to be a point of very high pressure because you have the blades close by pushing fluid into that area. And then, yeah, you just want to make it sort of rounded so that the fluid flows around it instead of getting turbulent. But yeah, I've usually just leave cutwater default. And then inducer, if we want to add an inducer, which will increase our efficiency considerably, we can add that in CF Turbo. I found 20%, 25% is a limit on our energy fraction because CF Turbo, once you start getting into 30%, of your energy is going to your inducer, CF Turbo starts complaining about, swirl angles and your fluid is cavitating and doing weird things. So I keep it under 20. I think the reason for that is something to do with the way CF Turbo handles blade angles when it designs your inducer. So if you go above 20, the blade angles get to a point where CF Turbo can't design them or it can't automatically figure them out. And because I don't understand what the blade angle should be, I like to keep things under 20% so that CF Turbo can do some of the inducer blade angle work for me.
Probably getting to the point where it's probably like getting out of the zone where an inducer would be the optimal machine, right? Like
Yeah.
too much of your pressurized to your inducer, then you might as well make it
make it an impeller. Yeah, that's probably what's going on. But yeah, if we're 3D printing, we could maybe stick an inducer on there. I think it's something to look into. And then, yeah, for running an ANSYS, we're going to get into this. When you are in CF Turbo and you're trying to set up an ANSYS run, you'll want to add an extension to your impeller because if the blades go right to the edge of the impeller, then CF Turbo can't, or Turbo Grid in ANSYS can't handle it. So yeah, what happens there is, yeah, Turbo Grid just won't run. And it's really kind of annoying, but yeah, you want to have this extension. So what it does is it extends your hub and your shroud over your blade so the blade doesn't go all the way to the end. And because of that, you can actually run this thing in ANSYS.